All right, this video is on how do we use the KSP to predict whether or not a precipitate is going to form in a double displacement reaction. So this is a bit of a throwback to what we did in grade 11. And so one of the things that we used last year was our solubility rules. And we looked at the different kinds of ions, and they were either soluble or insoluble. And but now with understanding how equilibrium works, we end up, when we have a precipitate forming, an equilibrium setup where the solid precipitate and the ions in solution kind of keep going in and out of solution. So the ions go to the crystal form, the ions go back into solution, and there's an equilibrium of that process set up where the forward and reverse rates are the same. When that equilibrium is set up, then we have the ability to determine an equilibrium constant, which we call the solubility product, or the KSP. If we know some concentrations of these solutions, then we can use what we call the trial ion product in order to compare it to the KSP and therefore determine whether or not we're actually going to get a precipitate forming. So the scenarios that we encounter are where our trial ion product is greater than the KSP, and in that case we get a saturated solution and a precipitate will form at the bottom of the beaker. If the Q value is the same as the KSP, which by the way is very rare, we get a situation where we have a saturated solution just. So all of the ions are dissolved, so solution is saturated, and we don't have any precipitate forming because all of the ions have gone into solution. And then we have the third situation where Q is less than KSP, and in that case we have an unsaturated solution and also no precipitate will form. So let's do a couple of examples. So the first one here, will a precipitate of lead 2 sulfate form if 100 milliliters of a 1 times 10 to the minus 3 mole per liter lead 2 nitrate is added to 100 milliliters of a 2 times 10 to the minus 3 molar magnesium sulfate solution. So if we mix these two solutions together, we get a reaction that looks like this. And so using our solubility rules last year, we would have predicted that the lead 2 sulfate is the solid precipitate. The problem is that these quantities are very low concentrations, okay? And so the question then here has to be are they so low that we may not actually get a precipitate? Because although we say that this is an insoluble precipitate, it is ever so slightly soluble. And so very small quantities of the ions will still remain in solution. And so because of that KSP value being times 10 to the minus 7, that tells us most of what we're going to get is going to stay as the solid lead 2 sulfate, and only a very, very small part will go into the ions. Right? So what we need to do then is figure out, okay, what's going to be our concentration of each of those ions. So the number of moles of the lead 2 plus ions works out to 1 times 10 to the minus 4 moles. The number of moles of the magnesium sulfate, or the sulfate ions, is going to be 2 times 10 to the minus 4 moles. So now we can use the volumes, right? So we had 100 milliliters of each, so when we mix them together we get 200 milliliters. So we're going to divide that number of moles by the 200 milliliters. And that gives us 5 times 10 to the minus 3 molar of lead 2 plus ions and 1 times 10 to the minus 3 molar of sulfate ions. All right, so now we use that in our solubility product. We figure out our trial ion quotient. And so that's going to be 5 times 10 to the minus 3 times 1 times 10 to the minus 3 gives us 5 times 10 to the minus 6. Now this number is greater than our 6.3 times 10 to the minus 7 KSP value, and so therefore we're going to get a precipitate forming. Okay, so there is enough of a concentration of these ions to form precipitate. Another example. Tap water contains chloride ions at a concentration of 0.0000500 molar. Will a precipitate of silver chloride form if we put 0.0025 grams of silver nitrate into this 800 milliliters of tap water? All right, so same idea. Look at our reaction equation. So we would assume that the silver chloride would be our precipitate. Find the number of moles of the silver ions from the number of moles of silver nitrate. Right, so it's a 1-to-1 ratio. So that means we're going to have a concentration of 1.47-ish times 10 to the minus 5 moles. For chloride ions, we are given that in the question, 0.0005 moles per liter. So we also already have that concentration. So now we need the concentration of the silver ions, number of moles divided by volume. It's 0.8 liters. And so we get 1.8-ish times 10 to the minus 5 molar. Calculate our ion product quotient, and we get 9.2 times 10 to the minus 9. And so comparing that to the KSP, it's greater than the KSP. And so we've got a precipitate forming. Okay. One more example. Will a precipitate form if we get 50 milliliters of a 0.01 molar lead to nitrate added to 20 milliliters of 0.4 molar sodium chloride solution? Same process again. Figure out the reaction equation. So we're looking at lead and chloride ions, lead 2 plus and chloride ions. The number of moles of the lead 2 plus ions, concentration times volume, gives us 0.0005 moles. Number of moles of the chloride ions, same thing, 0.4 times 0.02 gives us 0.008 moles. Because we're adding these volumes together, all right, we're going to get 70 milliliters, so that's going to be 0.005 divided by 0.07 gives us a 0.007-ish molar concentration of lead 2 plus ions. 0.008 divided by the 0.07 liters gives us a 0.114-ish molar of chloride ions. Our ion product quotient gives us 9.3-ish times 10 to the minus 5. Comparing that to the KSP, it's greater than the KSP, which is 1.7 times 10 to the minus 5. And so therefore we will get a precipitate in this case as well. Okay. All right, try these questions for homework, and we will discuss them with any problems you have in class.